Okay, so we're going to start the actual lecture proper now. So this is a lecture about water. So water is really important, and particularly the chemical properties of water are really important for enabling the Earth to work, for enabling life to work. So we wouldn't have liquid water on the surface of the Earth if it wasn't for the special chemical properties of water, which we kind of like are going to look at today. Okay, so if we didn't have liquid water on the Earth, things like life, so this is a cell kind of dividing, that wouldn't be possible if we didn't have liquid water at the surface of the Earth. We wouldn't have things like plate tectonics, couldn't exist without water at the surface of the Earth. So it would be a very, very different planet we wouldn't be living on if water didn't have this peculiar chemistry which we're going to look at today. So this is a table of lots of numbers, which I don't expect anybody to remember, but just to point out that most of the Earth's water is in the atmosphere. That's actually not true. Most of it is actually in the deep mantle. Okay, the mantle is very, very big. It's got a very low concentration of water. We don't really need to worry about that because that's staying down there. But over very, very long planetary evolution scales, that's where the water is. But for our purposes, this is, of course, an oceanography. So, of course, we're going to say that the most important source of water is the oceans. That is, of course, salt water, which is, salty, not so good for drinking, but is great for being in the ocean and doing oceany things. And that saltiness is important, and we'll see that later on today. Okay, so there is other things. So the atmosphere's got some water in rivers, biosphere, all that kind of things. But most of the water is in the ocean. Okay, so all of the next few slides will be a little bit of a recap of the video which I asked you guys to watch before. So there are supposedly 66 students on the course and approximately 33 views of the video since I kind of told you to look at it. So I understand that not all of you will have seen it. But just to quickly recap, so atoms have got a nucleus which is positively charged. If I give myself a little pointer here. Pointer options, pointer. Okay, so an nucleus of atoms are typically positively charged. Those are surrounded by negatively charged electrons. And the molecule of water is made up of one oxygen, okay, which has 8 electrons around it, and 2 hydrogens, okay, each with 1 electron kind of spinning around it. And the important thing is that when atoms don't really like having an odd number of electrons in their outer shell. They like their electrons to be paired together, and ideally they like their electron shells to be full. So this electron shell of hydrogen likes to have 2 electrons in it. It's only got 1, and the oxygen likes to have 8 in it, and it's only got 6. So those kind of bonds get actually, I won't skip over that, so those circular orbitals of electrons, that's kind of bullshit. So water molecules tend to bond like this, where you've got these covalent bonds where these electrons are shared between the atoms so that the hydrogen now has 2 electrons in its orbital, outer orbital, and the oxygen now has 8. Okay? So this has the effect of pulling the electrons away from this side of the hydrogen atom and this side of the hydrogen atom, which makes, because you've got a positive nucleus here, makes these little bits up here more positive, and the bottom of the molecule more negative. Okay. So that polar nature of the molecule leads to this concept of hydrogen bonding, where the different ends, the positive end and the negative end of the water molecule, effectively bond to each other. Okay, and these intermolecular bonds are what give water its kind of special properties. And that's what we're going to be talking about for a lot of today. So the graph at the top here is boiling point of a bunch of molecules that are a little bit like water. So H2O, this is water here, hydrogen sulfide, hydrogen selenide, and hydrogen telluride. So they're very similar in terms of their structure, okay? But they don't have hydrogen bonds, okay? Because the polarity of the molecule is less than for water. Now, this means that we have, so this is kind of molecular weight across the bottom, boiling point and melting point. So you can see that water both boils and melts at a much higher temperature than it would if it didn't have those hydrogen bonds. So we'd expect it to be kind of down here. And that would mean that at the surface temperature of the Earth, which is approximately kind of 15 degrees Celsius, water should be a gas, but it's not, it's a liquid. Okay? Another kind of point about these is that the boiling point and the boiling point up here and the freezing point are a long way apart, okay, compared to the other compounds. That means that water is liquid over a very wide range of temperatures, and that's also super important. Okay? And that's because we have these intermolecular bonds between water molecules kind of adding to that attraction, so that means that it's harder to pull apart one molecule out of this to, say, evaporate it off into a gas. Okay, so I've been through that. So this is stuff which should be in your handout, which kind of like summarizes kind of what I've just said. So I'm not going to go through this in too much detail. Just to say that these hydrogen bonds are really important for determining the structure of the different phases of water. So gaseous water, there are no hydrogen bonds going on. The molecules are essentially free to move around in that gas. But in a solid, the individual kind of molecules of water, so these little blue circles here are kind of, they should have these little tiny little hydrogens on the end of them. Okay? So each one of these is a water molecule, and they're held in this kind of rigid, arranged lattice by the intermolecular bonds, by the hydrogen bonds. Okay? And even in water, okay, so you might think of the water as the molecules are free to move around, but they kind of stay in their container rather than being allowed to evaporate out. You still have some hydrogen bonds between molecules, even in water. So water doesn't actually behave as if it were a kind of like a soup of individual water molecules. Okay? It's actually behaving more like I guess it's more like a claggy casserole of molecules, where you've got kind of lots of water molecules clumped together, okay, held together by these hydrogen bonds, and these bigger clumps of water are allowed to kind of move around, okay? And that is really important for some of the properties that we'll see today. Okay, so I think, this might not work with the pointer. Pointer options. Okay, so this is the kind of thing. So this is what we're looking at, the molecules of water in water, and you see they're kind of jiggling around because they've got some energy, but they're not completely allowed to move around freely. They're kind of almost held in place. And these kind of little sticks in between them are these hydrogen bonds that are kind of holding the molecules kind of semily in place. Okay, they're not completely fixed in place, but they are kind of it makes the liquid, okay, a lot stickier. It's a lot harder to move your hand through kind of like a glass of water than it is if you had a glass of alcohol, for instance. It's an experiment that you can perhaps do in your own time. So this is a similar run of a molecular simulation, but now these water molecules are kind of moving around. The time scale is slightly different on this. And they're kind of being held in place, and the temperature in this simulation is being reduced, and the water's starting to freeze, and these sticks now are starting to hold together the water molecules in a rigid lattice. Okay? So they're now kind of held together. They're still jiggling around a little bit because they've got some temperature, and that's what temperature is. It's the kind of the average kinetic energy of the molecules. But you can see now the hydrogen bonds are holding the water molecules together in this rigid lattice. Okay, and this is a nice example. This is one of my collaborators looking in a cave in Siberia, and the water is freezing from the gas phase onto the surface of the cave, forming these beautiful rigid crystals of ice. Okay, and that structure is due to the hydrogen bonds holding the water in this very rigid thing. Okay. So just a quick recap on some of the properties of matter that I've been kind of talking about. So the molecular motion, so how much a molecule is vibrating or can move around, okay, that is its temperature. Okay, so the more a molecule can move around, the more the hotter it is. So that's different to heat content, which is something slightly different. So in solids, the atoms are kind of held in place. In liquids, they kind of allow to move around amongst each other, but they're still kind of contained within their container. And in gases, the individual molecules are completely free to move around. And melting and freezing are the transitions between these phases. Evaporation is taking liquid to gas. Condensation is the reverse. Now, the important thing is that the hydrogen bond modifies all of these properties. Okay, so it makes the water more viscous, so it's harder to move through it because it's kind of held together by these hydrogen bonds. It has a whole bunch of other different properties as well. Okay, but these large clumps of water are really important, and we'll see that with the experiment thing. So one of the things that these hydrogen bonds are really important for are surface tension. Okay, so imagine that each of these little dots on here is a water molecule that's being kind of held on to other water molecules via hydrogen bonds. Okay, except at the surface, that bonding energy, kind of bonding potential from each molecule, can't act in all directions because there's no water above it. So that means that the bonding has to be stronger kind of along the surface of the water. And this is really important if you're a kind of a pond skater, or it's important for like the physics of how droplets of water form. So if you were interested in there being clouds on Earth, you really need to understand this bonding process and the properties of water that are determining how much surface tension we get, which determines how big raindrops can get, or the smallest size of raindrops, and how they nucleate. Okay, so I've already mentioned this, but just to go into it in a little bit more detail, so that the melting points and boiling points are much higher. Okay, so and there's a bigger gap with water in between the melting and the boiling points, and that's because so if you imagine if you're heating some water up from an ice, okay, you have to break those hydrogen bonds. They're very strong compared to other intermolecular bonds like Van der Waals bonds. So I think I mentioned in the video they're approximately a tenth or a twelfth of the strength of a regular intramolecular bond. Okay, so they're very, very strong bonds. So you have to heat up your solid quite a lot, up to 0 degrees Celsius, to start to break some of those bonds apart enough that the clumps of effectively ice become small enough that they can start to flow. And that's what water is. And now, once you've made water, the hydrogen bonds still exist between, or some hydrogen bonds still exist between water molecules. And as you add energy, as you start to increase the temperature, all you're doing is you're breaking apart some more of those hydrogen bonds. So rather than actually give the individual atoms enough energy to escape out of the water into the gas, all you're doing is breaking more and more hydrogen bonds, which is making those clumps of water maybe a little bit smaller, okay, but you're not allowing it to become a gas yet. So it's that extra energy in the intermolecular bonds that are causing this large gap between the melting and the boiling point of water. Okay, so that's what allows it to stay liquid over such a wide range of temperature, which is really key. Yeah, so this is just to demonstrate what actually temperature is. So temperature is effectively the average kinetic energy of the molecules moving around in your substance. So if you increase the energy, okay, you are making those things move around faster. But if some of that energy has to go into breaking bonds rather than making things move around faster, you put more energy into the system, but its temperature doesn't go up as much. Okay. So these graphs over on the left are some of the other properties of thermodynamic properties of water, other than just the boiling point and the melting point, but they're the amount of energy that you have to put into the substance to change it from solid to liquid, which is the which is this blue line at the bottom, or the amount that you have to put in to take it from liquid to gas. So that's the enthalpy of evaporation at the top. So you can see for water to take something from liquid to gas, not only is it hard to increase the temperature, but there's an even stronger barrier that you have to go through, okay, to convert something from liquid to gas. So that's the enthalpy of evaporation. Okay, so we need to put a lot of energy in to change either the temperature or the state of water, which is why it stays at a liquid in so much of the Earth. Okay, so hydrogen bond is responsible for that. This equation that's randomly appeared in the middle of the slide is a bit annoying, but is irrelevant. I mentioned that it's hard to increase the temperature and hard to change the state. So hard to increase the temperature is effectively a thing called heat capacity. So that's the amount of energy that you need to put into a substance to raise its temperature. Okay? So that can be thought of effectively in a slightly different way as the amount of energy something can store in terms of heat. So like a storage heater that you might have in an old flat in Edinburgh is got a very high heat capacity because it can store a lot of heat energy, okay? And that heat energy can then be extracted out of it at a later date. So this is important globally. So this is a map of the surface temperature of the ocean. Okay, and you can see that the equator is warmer than the poles. Okay, so that's up to 30 degrees and down to 0 degrees at the poles. Now, that heat has to get from the equator to the poles somehow. Otherwise, this region would get super, super cold in winter, and we'd end up with a very, very icy ocean. Also, we need to remove heat from the equator, because if we didn't remove heat from the equator, it would just get hotter and hotter and hotter, because that's where the sun is delivering most of its energy. So there's a transport of heat from the equator to the poles, which I think you might be covering or have covered in physical oceanography. Okay? And the reason why the ocean is so good at doing this is because it has a high heat capacity. You can put a lot of energy into water in the equator, and you move that into a colder region of the Earth by advection, and then that heat can get out again. So heat capacity is really important for kind of spreading heat around the Earth. It's responsible for kind of like our weather and climate. So understanding how you can store heat in the ocean is super important. Okay, so this is a little close-up of how some of that heat is taken from the Caribbean down here, and you can see the Gulf Stream, this kind of ribbon of warm water heading off up into the Atlantic. That's just transporting huge quantities of heat north. Okay. Okay, so one of the things that, one of the properties of water that we're going to have a quick demonstration of, hopefully, is when water gets hot, when it starts to, or when any substance starts to get hot, it tends to expand. So I have here, hopefully, that won't I'll put my, it's not science unless you've got safety glasses on with an unknown liquid on them. There we go, I'm super safe now. So if I pour some hot water in there, should be hot, yeah, and always wear dark clothing if you're dealing with food colouring, so you don't have to worry about getting it on you. So if I put a little bit of food dye in here so we can kind of see its colour. There we go. That's fun. Now, if I was to get some cold water and put that on top, you can see this from the back, yeah? Okay, all the people that didn't turn up are not seeing it because the camera's not pointing towards it, so it sucks to be them. Well, I'm sure they're having a fantastic time doing whatever it is that they're doing. So I've got here, I've got a bit of my field notebook, which I've cut a hole in. If I put that on there, I've not done this before, so it might not work. And then if I do the kind of like the old trick of holding the water upside down, well, that works on there. And then if I pull that out of there, you can kind of see the hot water is now flowing upwards into the glass thing. Yeah? So that implies that the hot water is less dense than the cold water, okay? And that's because it's absorbed some heat energy, and those molecules, water molecules, are now vibrating a little bit more, and that's holding them a bit further apart. Okay? Yeah, now I'm fucked. So I'll just do that. So now I'm going to do it the other way around. So hopefully, if just going to make that redder so it's more obvious. Redder, yeah, we all like red, don't we? And just make sure that that is super topped up. So if I do it the other way round now, he says confidently. Dun, 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 dun. So, what do you think will happen when I pull out the card? Other than I'll make a mess and cover myself in red. Is the water going to stay on the top, or is it going to sink down? Stay on top. Okay, good. Somebody has been learning. Excellent. So if we just take those away now. Yeah, it's kind of staying at the top. Yeah. So what I'm going to do is I'm going to put two more out. So if I just fill these up with cold water and make myself some hot water. Might be a bit too much red. Oh, I really am covering myself in red here, aren't I? Oh well. So if I put these out somewhere where you can see them, yeah, if you might get red on you. If you and then if I put some of the hot water gently on top, you can kind of see that it kind of floats towards the top of the glass. Yes? Okay, we'll leave that there and see if it does its thing. You just leave that for the next lecturer to come in and... Okay, right. So we'll see if this works. I'm so red. Right. So we know that now that water gets less dense as we heat it up. Okay. But the water here already started at the cold water was kind of room temperature, maybe 20 or so degrees. So water has this very strange behavior that actually gets very, very cold. Okay, the density actually starts to increase a little bit more. Okay, so this is a graph kind of explaining a little bit about what we've done. So you can see here that the temperature along the bottom and the density across the upness. So the experiment that we've just done now has been over towards the right-hand side of this graph. Okay, so as we've increased the temperature, okay, we've decreased the density. It floats on top. Okay, but as we cool it down, so very, very cold, it actually starts to get a little bit more dense. Okay, and what's happening here is that as it cools down, more of these intermolecular bonds are starting to form, and we're making these clusters of water, okay, bigger and bigger and bigger. And those clusters of water, because they're held together by these hydrogen bonds, Okay, so the clusters don't actually kind of look like this with a kind of a random jumble of molecules held together. And actually this is quite a misleading kind of figure here, because this makes it look like actually they're held together closer in the clumps than outside of the clumps, when actually the clumps are a little bit like ice, whereas the molecules are held a little bit further apart by being in this regular structure. Okay, so that means as we cool the water down, these clumps of water molecules get bigger and bigger and bigger, and that causes them to behave a little bit more like ice. Okay, a way of thinking about it, which is incorrect, is that the water is effectively little tiny clumps of ice kind of held together in kind of water. Okay? So we have this thing where we've got the maximum density of water at 4 degrees Celsius. And this is really important for terrestrial aquatic systems. Because if you think about it, if you've got a lake, okay, and that lake's maybe freezing in winter, you're removing heat from the lake at the surface, okay, as you kind of like evaporate a bit of water, or you actually just have heat transport from the lake to the cold atmosphere. So that means the surface of the lake starts to get colder and colder and colder. Okay, so we would move kind of along this line here, we're getting colder and colder, and the water is becoming denser and denser and denser. Okay? Now if you cool the surface of the lake, okay, it becomes kind of it becomes denser, so the water would then sink to the bottom of the lake. Okay? Which means that the whole lake would cool down to 4 degrees Celsius before it could start to freeze. Okay? Whereas if you actually look what starts to happen, once you get the lake to 4 degrees Celsius, okay, you start removing heat from that, it means that your lake, that as you cool the surface of the lake down even more, okay, the water gets less dense, so it stays at the surface of the lake, where it can cool down even more and form ice, which means it's a lot easier to form ice on a lake, yeah, than it would be if the water kept on getting more dense as it cooled down. And this is really important because actually that layer of ice then insulates the rest of the lake from any more cooling. So if this didn't happen, okay, if we didn't have this change of the relationship between temperature and density on lakes, it means that lakes would get colder and colder and colder. Okay, the surface would get colder and that surface water would become more dense, it would sink to the bottom of the lake, and then the whole lake would get to very close to freezing. And then you'd run into a situation where you could actually freeze the whole depth of your lake. Whereas actually, what you tend to do is you freeze just the surface of the lake, okay? And then that means that you then can't transport any more heat out into the atmosphere. Okay? Which means that life can survive in lakes through the winter, which is nice if you are a fish that lives in a lake. Okay, so this is the thing that water reaches its maximum density at 4 degrees Celsius almost. Okay? Now, let's think about whether that happens in the ocean. So, one of the things that the ocean has is lots of salts dissolved in it. The most common salt is sodium chloride, and we'll come on to the next lecture when we'll talk more about the salts in the ocean. But the reason why that there is so much salt dissolved in the ocean is because water is a really good solvent. Okay? So what water does, because it's a polar molecule, it can come along to a kind of a salt crystal, and it can kind of pluck out. Its positive end can attract and bind onto the negative chlorines and pluck them out of the crystal. And then once they've been plucked out, and once that ion is floating around in the water, it gets surrounded by other water molecules. Okay, because it's kind of a negatively charged chlorine ion, surrounded by the positive ends of water molecules, which would leave those ends of water molecules kind of sticking out, which would then attract more water molecules. So you end up with the ions basically in the middle of these big clumps of water. So what this means is that those ions then, it's very hard for them to find other ions to pair up with. So once you've dissolved it, it's then very, very soluble. That means we can put a lot of dissolved salts in the ocean. Oh, and this might be a... No, there was a video there, it doesn't so matter. But water basically plucks salts apart and then keeps them in solution. Okay, so let's think about how this salt that's dissolved in water affects this freezing process in the ocean. So this is kind of sea ice forming in the ocean, I think in the Arctic, and this is a lake somewhere in Scotland. I think it's in Edinburgh, actually. Anyway, it's in the National Gallery. Go and see it. It's a very nice painting. So we had this diagram before showing you that water reached its maximum density as it cooled down, and then we started building these large clumps of water which stopped it getting denser, okay, which means the density went down. But that behavior changes as we add more and more salt. Okay? So I think I've made a different plot of this. So this diagram is quite hard to get your head round. So I've taken this figure and I've kind of flattened it out onto the bottom of this. We've now got a three-dimensional plot where we've got salinity is increasing along this way, temperature is increasing kind of into the board, and then the density is increasing upwards. Okay? So when you've got pure water, which is this end, no salt dissolved in it, then you get a maximum density at this 4 degrees Celsius. And what this red line is that tracking that maximum hump in density. So as you add more salt, okay, what's happening is that maximum density is reducing. Okay? And the reason for that is that the salt, okay, is interacting with these clumps of water, okay, and stopping them kind of holding the water apart. Okay, so it's modifying that. You can also see that the freezing point is reducing as well. So there's 0, there's kind of 30 degrees, 30%, 30 per mil salt, so 3% salt, and the melting point is reduced. Okay. So what the important thing on this is to think about. So if you've got, say, fresh water, it's that first blue arrow up here. So as we cool down, we get to a maximum density, and then we get less dense, and then we freeze. But at some value of around 24 parts per thousand salt, okay, you reach a point where as you cool down, okay, the water carries on increasing with density, and then it freezes. It doesn't get to that maximum density before it can freeze. Now this is important because the ocean is of this salinity. So it means that that maximum density at 4 degrees doesn't apply to the ocean. Okay? So this means that as we cool down the surface of the ocean, the water will always get more dense and then sink down to the bottom. Which does kind of mean that we might be able to freeze the whole ocean if we keep the planet cold enough for long enough. But because the ocean is really big, that's not going to happen. Okay? What it does mean, though, is that it's actually now harder to form sea ice in the ocean because you don't keep that cold water at the surface. As soon as you cool it down, it tends to sink to the bottom. So the saltier the ocean is, the harder it is to form that sea ice. Just a little aside here. So that this basically this is another way of plotting that last graph of this is pure water, this is actually pure salt. Okay, so we were looking at 3% salt, so we were just up to here, and that's that little red line on the phase diagram of water here. So as you mix together two chemicals, water and salt, so water freezes at 0 degrees, salt freezes at a couple of 100 degrees. Okay, if you ever try to melt salt, don't do that, it's really hard. But if you mix those two chemicals together, their melting point follows a curve something like this. So some of the geologists might have seen something like this before in something that's called a eutectic. But basically, just kind of to point out that at some point, okay, it doesn't matter how much salt you add, the melting point doesn't come down anymore. Okay, so this is one of the reasons why we don't salt the roads in Russia or Canada, because it's too cold for adding salt to ice to kind of raise its melting point, lower its melting point, sorry. But that's just an aside thingy. Okay, so salt modifies the properties of water a little bit. Okay, we've covered the contrast between how sea ice forms. You always read that in your own time. So talk a little bit now about this process called diffusion. Okay, so this is if you've got any substance, really, it could be a gas, it could be a liquid, or even can be a solid. If the concentration of something in that solid, liquid, or gas is not uniform, there's those concentration anomalies will want to even out over time. Okay, so so if you add a bit of dye to some water, over time it will want to kind of even out those concentration variables and be well mixed. Okay, if you fart in a lift, right, that smell will kind of gradually fill the whole lift. Even in solids, this happens as well. So if you have some crystals that are maybe got some different calcium to aluminium ratios over enough geological time, potentially hundreds of millions of years, those concentration gradients may well even themselves out. So diffusion through water is actually quite interesting. Okay. So actually, if we go and have a look back at our examples of stuff that's happened. So if you look at the bottom of the layer of, it hasn't done it. Oh, this one has. Let's see if I can bring this up. Yes, will that make that bigger? Okay, so you might be able to see. Can you see that thingy? Bring this down to here. You can't really make it out. But if you look, I'll leave it up at the end. You can come and look at it. The bottom layer of red has started to go wavy up and down. Okay, which should have looked like this. Okay, so we're actually getting some mixing between the surface layer and the bottom layer. I think I've linked a video of me doing this experiment more successfully on Learn. So what's happening here? Why is the seemingly low density warm water sinking down into the cold density water? Okay, it's not evenly diffusing. Okay, it's not moving constantly. We're getting this very, very undulated contact. So what's happening here is that we get some initial kind of disturbance in the layer, the boundary between the two layers. And then two things want to happen. Okay, so the top layer is hot. Okay, it's hotter water, and that heat doesn't want to stay in the top. It wants to be evenly distributed around the whole thing, right? So, and the way that happens is that you start. So the heat is just the kinetic energy of a water molecule. Okay, and what happens is that bumps into the next water molecule and shakes that one, shakes it along. Okay, and eventually that amount of vibration is then evened out over the whole substance. But actually, this water hasn't just got extra heat in it, okay? It's got some red dye in it. And that red dye acts a little bit like salt, okay? So if you add salt to fresh water, that increases the density of that water. You're basically putting more atoms in between the spaces of the water molecules. So that makes it more dense. Okay, so if you have salty water, that should sink to the bottom. So at the moment, the water is the heat in the water is overcoming the saltiness to keep it at the top. But if you imagine that we've got some salt in the top and that wants to diffuse down through into the bottom layer, it has to get past all of these molecules. It's not just shaking one and that moves on to the next one, that moves on to the next one. You've physically got to get the ion of salt, and it's got to work its way through all of these atoms that are trying to grab onto it. Okay? So that means that diffusion works a lot more slowly for salts than it does for heat. Okay? And what that means is that if you've got a slight kind of anomaly in the surface between the hot and the cold water, the heat will diffuse from the hot place to the cold place very easily, but the salt won't. So that'll make this bit of water here, okay, cold and salty, so it will start to sink down, whereas the water up here will stay warm and salty. Okay, so there's a slightly better video of that happening on the interweb. Okay, so tomorrow we're going to talk a little bit about the salinity of the ocean and recycling of water, but effectively the ocean is salty, okay, because the rivers bring in fresh water to the ocean, but that fresh water has got a small amount of salt in it, okay, but the oceans are very, very salty, so how can you make this very salty when you're continually adding fresh water to it? And the answer is that when you evaporate the water, you only evaporate the water and you leave behind those small amounts of salt, so the ocean gradually gets more and more salty. So we'll talk a bit more about that tomorrow. So just to quickly, I've been talking about salinity and the amount of salt in. So the actual definition of what salinity is the amount of salts, so not just sodium and chlorine, but the total amount of dissolved stuff in the ocean, in a grams per kilogram of water. Okay, so and the more of that you have, the denser that the water becomes. Okay, it's units. You might sometimes see this practical salinity units, but if you have grams divided by kilograms, there are no units. So it's quite often referred to as parts per thousand. So for every part of water, how many 1,000 parts of water, how many parts of salts do you have? And just like the heat, that salt is distributed unevenly across the oceans. And that affects its density and its physical properties. So you've done this with physical oceanography, so the saltier water gets, the heavier it gets. And this pattern of where water is salty and where water is not salty is driven by evaporation and precipitation. Okay, so where we have lots of rain on the equator, you have a slight salinity low, where you have kind of essentially the deserts of the ocean, these oligotrophic gyres, we have a lot more kind of like evaporation than we have precipitation, so the water gets more salty there. Whereas at the high latitudes where it rains a lot, you can kind of see maybe coming out of big rivers, you have sources of fresh water that's making it less salty. Okay. Okay, so that's the end of today's lecture. So there are a couple of slides at the end here. There's this one and this one, which is kind of stuff that you should know. Okay, so if you don't know the answers to these things I guess should have question marks at the end of them, then these are perhaps things you might want to start discussing on the discussion forum to make sure that you do know them. Okay, so if you're on your way out, do come by the... it is kind of... You have to get like quite close to be able to see these kind of fingers coming down. So actually, this process of diffusion being slightly different between salt and heat is actually, it's a process that's happening on the scale of maybe a centimetre or so, a couple of millimetres. But in the ocean, it's responsible for mixing across hundreds of metres in the ocean. So it's a really important process in the ocean from physical oceanography kind of point of view. So have a look at that. And I'll see you after Creative Learning Festival of Week, which, if you've not signed up for stuff during that week, do sign up for it. It's an opportunity to do kind of interesting and wacky things, and some of the courses will be also relevant to your studies. So do that. And if you want to go to the geology ball, I think they're selling tickets in the place for the bottom of the stairs. It'll be fun. Kate Saunders is talking, so it'll be hilarious. So do that.